Oh, welcome. This brief video is going to give an overview of some of the new features in GeoClaw as of version 5.7.0 of Clawpack, which was released earlier in May 2020. This is going to be a repeat of a brief talk I gave at a workshop we had last week, GeoClaw Developers Workshop and Hackathon, which many people joined. And I intended to record it then, but I forgot to press the record button, so I'm redoing it. But I have the benefit now of knowing some of the questions and things people were interested in hearing more about, so I'll try to answer those also as I go along. Let me go ahead and turn my video off so that you can see the screen a little better. So there's a few slides on this webpage, which is under clawpack.org/geoclawdev-2020. So you can download these slides from that website. And the slides have some live links in them to things that may be useful that I'll be talking about. And in particular, there's a number of release notes from the 5.7.0 release that have links to some of the documentation pages that discuss these issues in more detail. We also have a gallery on the clawpack.org site, which includes also a number of Jupyter notebooks, which have been developed in particular to describe some of the new features in 5.7.0. And I'll mention some of those as we go along too. So one new feature is that we now allow particle tracking as part of our solution to the shallow water equations. So we're still solving the two-dimensional shallow water equations typically, but the velocity field that comes out of that can be used to push a set of massless tracer particles. So each time step, the location of a set of particles is updated. And this is implemented in the form of what we call Lagrangian gauges. So we have the ability in GeoClaw or Clawpack more generally to put a set of gauges in at locations where we want to record the depth and the velocity of the water. And in the past, these have always been stationary locations. Now they're allowed to be Lagrangian gauges that flow with the fluid. So a caveat, these are massless particles. They're intended primarily to sort of visualize the flow. You can interpret them in some cases as how particles in the water, like debris or boats even, would actually be carried in a tsunami. But they really represent massless or very small mass particles, and they don't properly model the interaction of a particle with large mass with the flow. So let me show one example, and then I'll talk about that a little bit more. So this Port Angeles Harbor, this is a simulation that we did a location on the Strait of Juan de Fuca in Washington State, where a tsunami comes in from the Pacific Ocean from the west here, and it goes past this spit at this hook that sticks out here, and this is about a mile long or so, so this is a very large spit of land. There's actually a large Coast Guard station at the end here with an airfield and several ships typically docked here. And one thing that you see is that as the tsunami comes by, it generates a lot of vorticity near the end of this spit, and you can get very large velocities and eddies that form in the water and move away from this spit. What's being shown with the color here is the speed of the water, the current speed measured in knots. So going up to 8 knots, which is considered a quite dangerous current. And then you get these very localized vortices or eddies that can move off in many different directions from the end of the spit. So these kind of simulations can really sort of help you visualize the flow. Let's go back and run this one again from the beginning. But again, these are really massless particles, so they only approximately show how an actual boat might move during the tsunami. But still, it's very informative in terms of what can happen here. And we found that this is very useful in both understanding the dynamics of a tsunami and also in communicating with people in the Coast Guard, for example, or other people in the communities, mariners, people who have small boats and who might think, well, if there's a tsunami, all I have to do is hop in my boat and go out away from shore, and then I'll be safe. But this helps convince people that that's actually typically a very bad idea in a tsunami. There's also here, there's a boat marina down here, which has lots of small sailboats and other pleasure craft in it. And we've done some other simulations with even a much smaller magnitude tsunami than the one that's shown here, where there's not any inundation at all of the downtown area, which is actually totally flooded here. But still, you get very strong currents in the entrance of this marina, and you see very strong high velocities there. So this is something that's, we're still kind of exploring the best ways to use it, but we found it a very useful device for certain things. There's a simpler example in the GeoClaw examples directory, which I will show just very briefly, which is flow of water past the island here. So it's just flow coming from left to right, going around this island. And again, these massless particles are sort of helping you visualize the complicated flow that's generated on the lee side of the island. These X's here are stationary gauges, so you can now specify for each gauge whether it's a stationary gauge at some fixed location where you're keeping track of the fluid velocity and depth, or whether it's one of these Lagrangian gauges. And there's some documentation to describe that that's linked here as well. So that's one new feature that we've been looking at. Another whole set of features that have been introduced have been really motivated by some of the recent work we've been doing in modeling tsunamis for the state of Washington. Washington state has a lot of coastline, both along the Pacific coast and then within the Puget Sound and the Salish Sea, the Strait of Juan de Fuca. There's something like 5,000 kilometers of coastline in Washington state, and it's all susceptible to tsunamis, either from the Cascadia subduction zone offshore or even deep in the Sound. Those waves can still come in, but there's also crustal faults like the Seattle Fault and the Tacoma Fault that run right across Puget Sound. And so there's a lot of coastline to deal with, and a lot of it is very complicated. And dealing with that properly has forced us to develop a lot of new features. So one of the links here is to this webpage that describes one of our recent modeling studies for portions of Island County and Skagit County in Washington. Island County is Whidbey Island, which is a very large island in the middle of Puget Sound here. Skagit County is on the mainland here and includes the Skagit Valley, which is very beautiful in the spring. Lots of tulip fields in this area that's colored pink in this particular image on the left. But the reason it's colored pink is it's also, like Holland, it has lots of tulip fields, but it also has lots of land that's below sea level and is protected by dikes. And so all of these pink areas, which is a total of about 200 square kilometers, is land that's below sea level and should be initially dry in a simulation, a tsunami simulation, because a smaller amplitude tsunami wouldn't inundate these areas at all. But a larger amplitude tsunami would overtop the dikes and inundate some of this farmland and some of the communities that are in here. So I actually have a Google Earth image. It's maybe a little easier to see if I can find that. Yeah, so this is Whidbey Island. Just if we zoom out to give you an idea of where we are, this is the Olympic Peninsula, Pacific Ocean, Strait of Juan de Fuca, Puget Sound in here, Seattle is down here, Vancouver, BC is up here, and we're looking at this area here between Whidbey Island and the Skagit Valley. And another new feature that we've been working on a lot is sort of better ways to display our results as PNG files embedded in KML files so that you can open them in Google Earth and zoom in as we're doing here. So one thing that we do in helping the state develop a new generation of tsunami inundation maps for the whole coastline is to keep track during the course of a simulation of the maximum flow depth at each point on some grid. And we call these FG max grids, fixed grids where we keep track of the maximum, fixed in the sense that this grid doesn't change even as we're using adaptive mesh refinement to follow a wave or to zoom in on particular areas only over part of the simulation. We have these fixed grids where we're keeping track of the maximum by updating every few time steps with whatever the current value is there. So in the past, we've also had FG max grids that were typically most easily specified as rectangles, some uniform grid in longitude latitude space. But as we start dealing with larger and larger areas, those rectangles become prohibitively large. And so one thing we've done is to develop a new set of algorithms for sort of identifying points that are close enough to the shore and low enough elevation that they might flood, and only keep track of the maximum inundation depth at those points. So we now have this ability to specify FG max grids that are not just every point on the grid, but every point on the grid that's been also selected to be below some elevation, for example. So what I'm showing here, it's a little hard to see maybe at the moment, but all of these colored points, whatever color they are points that were selected as FG max points for this particular simulation. And the ones where there's no coloring are either water points, in this case, where we were also keeping track of things, but here I'm showing the maximum depth, so it's only being shown on the points that were initially dry, or they were high enough elevation, like in here or over here, that we knew they would never get wet. And in this figure, all of the green points are ones that did not get wet during the simulation. They started out dry and they stayed dry for the entire simulation for this hypothetical Cascadia subduction zone tsunami coming into this area. All of the points that are colored when blue, red, or purple are points that did get wet. They started out dry, but they got wet during the simulation. And if we turn that layer off, we see that a lot of these areas are this farmland that I was talking about, much of which was initially below sea level, or at least below mean high water, the level at which we run our tsunami simulation, but that got wet during the course of the simulation. And so one issue that we've dealt with is how do we sort of identify initially what points should be dry because they're protected by dikes versus what points are connected to the water and should be wet. Because all of these regions in here, again, were initialized as dry, even though a lot of them were below mean high water. And so we've developed a new set of algorithms for doing that sort of thing. And that's sort of described in this documentation on marching front algorithms and forcing regions to be initially dry. So another thing that we've done is to introduce sort of a new class of data structures for specifying, say, our FG max grids or regions on which we want to do adaptive mesh refinement that we call ruled rectangles. So that was also motivated by the sort of topography that we're dealing with here on Whidbey Island and Skagit Valley. For this region, we had to model all of the areas that are enclosed in polygons here and that are labeled northwest, east, west, Skagit, and so on. But there were too many points here to do a single simulation and keep track of everything in a single simulation. And so we actually had to break this up into 6 different simulations, one for each of these regions. So for example, the east region on the east side of Whidbey Island, between Whidbey Island and Camano Island here, when we were simulating this area, we wanted to choose FG max points that only lay in this polygon. And then as we were doing the simulation, we wanted a higher level of adaptive refinement in this region than we needed perhaps on the west side of Whidbey Island. And so we want to be able to specify these polygons both as regions where we select FG max points and also as regions where we allow or force some higher level of adaptive refinement than elsewhere. So for a long time, we've had the capability of specifying regions, which we now call flag regions, regions where you're allowing or forcing some level of refinement that may be different from other regions. But in the past, those always had to be simple rectangles, and now we allow these more general polygons. So we don't allow an arbitrary polygon, because an arbitrary polygon, it's very difficult in general to figure out whether you're inside or outside the polygon. There are computational geometry algorithms for doing that, of course, but they're relatively expensive. And if we're looking at, for example, a region where we want to force some level of adaptive refinement, then every time we regrid, which might be every few time steps, we have to loop over every grid cell on the current patches and determine whether that grid cell should be refined to the next level. And so we have to determine whether every grid cell on each patch is inside or outside of one of these regions every time that we do regridding. And there can be literally tens of millions of grid points, grid cells in a single simulation of this sort. And if we're regridding every few time steps, we need a region that's very easy to check whether we're inside or outside. So a rectangle, it's very easy. You can just check your latitude and longitude and see if you're inside the rectangle. And these polygons are also relatively easy, much easier than a general polygon would be. And so this is this new data structure that we call ruled rectangles, which I won't say too much about, but you can read more about it on this documentation page. It basically allows you to specify a set of x values. For example, here the values 1, 2, 4, and 6 were specified. And then for each x value, a range of y values. So at x equals 1, from 0 to 4, at x equals 2, from 2 to 5, and so on. And then you can say in between those points, either you should connect them with linear segments to give a polygon like this, or you should sort of make a piecewise constant in between and just use the values, the range, the lower to upper range specified at x equals 1, all the way up to the next node 2, and then use the range that was specified there from 2 to 5, all the way up to the next node, which was at 4, and so on. And there's some contexts where it's nice to be able to use what's on the left, in particular for the regions that we were just looking at. Each one of these regions, where did it go to? Each one of these regions is exactly one of those ruled rectangles where we've either specified a set of longitudes and then a range of latitudes of each, or in the case of this northwest region, for example, we have a set of latitudes here, 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 and here, and then there's a range of longitudes at each latitude. So you can specify quite general polygons. They don't have to be convex even, but they do have some other restrictions on them. But once you've specified it in this framework, then it's very easy to tell whether you're inside or outside by first checking which one of these nodes you're between, and then checking whether you're between the lower and upper limit specified for that node. So by specifying just a few points and then connecting with piecewise linear, you can specify polygons like this. Sometimes you want polygons, though, that exactly cover a set of grid cells, and then this form is better. In particular, if you go down to the very bottom of this page, there's an example of such a region that was constructed actually starting with a topography DEM out in the ocean and saying we wanted to choose all of the points for the elevation, the topography, or the bathymetry was between some limits, and that allowed us to capture the relatively shallow continental shelf and a bit of the coastline without going up into the high mountains or out into the deep ocean, and cover sort of all of the grid cells that were within some range of elevations. This is a very convenient region to use as a flag region for adaptive refinement in cases where you're modeling a tsunami in the Pacific, because tsunamis tend to get trapped on the continental shelf. You get edge waves that can propagate up and down along the continental shelf long after the main wave has dissipated out in the ocean because of the changes in depth at the edge of the shelf. And so you might want to have a finer computational grid along the shelf that has to remain refined for many more hours than the refinement that you're using out in the ocean. And so this is an example of how to specify such a thing. And in this case, we've specified a ruled region by first specifying this range of elevations and then using this marching front algorithm, which I won't talk about too much, to kind of march from the shoreline both into deep water and onto land until you reach a certain elevation. The marching front algorithm was also originally developed to deal with this problem of identifying land that's behind the dike, and to march until you reach a dike, for example. So if you go to the forced cells to be initially dry documentation, there's an example here. This is another region, Washington State on Whidbey Island, in fact, where you can see this looks like dry land, but if you look at the elevation, it's below sea level here. And if we initialized GeoClaw by just filling in all of the topography up to mean high water, which is how we typically initialize, then it would put a big lake here, whereas instead there should be some dry land. So what we can do with this marching front algorithm is start out in the deep water and then march until we reach a given elevation and only mark adjacent cells as being part of the ocean if they're adjacent to a cell we've already marked and below our target elevation. So in this case, when we reach this ridge that runs along the coast here, the marching algorithm would stop, and we would have correctly identified that, in fact, go down here, all of these points in here are really dry land rather than points that should be initialized as wet cells. Okay, that's a very, very brief overview of some of the issues we've been looking at. I guess there's one other pointer here to specifying a varying initial sea level rather than specifying a single value of sea level that's used everywhere. There are cases where you want to perhaps have a lake on shore that's at a higher initial elevation than the water out in the ocean. And so this new capability allows you to do that more easily. Also, if there's uplift or subsidence of the coast during an earthquake, and you're not refining some area near the coast until later in the simulation, then maybe you don't want to initialize it to sea level, but instead to the subsided sea level if that part of the coast has subsided because the water near the coast has also subsided by the same amount. And so that was an issue that we were having in some areas too. So I won't say more about those, but the documentation describes some of those new features. Okay, so those are the things that I wanted to cover in this video. Again, I invite you to, if we go back here to the first page, the release notes for version 5.7.0 has a summary of some of the changes in each one of the ClawPack repositories with links to all of the diffs and all of the commits that were made from one release to the next, and also some links to some of the documentation pages that are relevant. So I will stop here and encourage you to play around with this, and by all means contact us if you have questions about any of these new features.